So we're going to start some year 13 work. Collisions in two dimensions. So this is further mechanics, and we are looking at momentum and the conservation of momentum, and we're going to look at kinetic energy, and using that we are going to see if the collision between objects is an elastic collision or an inelastic collision. Now, I found these notes online, and I think they're really good. Rather than me write them out again, I'm just going to go over them, and then I'm going to go over an example myself, added on to additional points that are onto your syllabus. So we're going to look at collisions in two dimensions, and a collision in two dimensions obeys the same rules as collisions in one dimension. So when we were looking at the conservation of momentum, the total momentum in each direction is always the same as before. And the total kinetic energy before and after are equal when it's an elastic collision, and when it's an inelastic collision, the total kinetic energy before is greater than the total kinetic energy after. Some of that energy has been transferred as thermal energy. Now, when we are looking at two dimensions, momentum, we will split into components depending on if it's two dimensions, it's x and y. So we will look at the momentum in x before and after. We will look at the momentum in y before and after. But when we are looking at kinetic energy, remember, energy is not a vector, so it doesn't have, it's a scalar property. So when we are using the velocities in the conservation of kinetic energy, but to see whether the collision is elastic or inelastic, we will use the magnitude of the velocity of the object rather than the x component, y component separately. And remember, momentum is a vector, which is why we have to separate the components out, whereas kinetic energy is a scalar. Now, I'll explain these notes with additions. So collisions in 2D, make these notes as you go along, and any additions if you feel necessary. So from mechanics in year 12, the first mechanics section that you looked at earlier on in the year, you looked at the conservation of momentum, but in one dimension. Okay. And remember, momentum is always conserved, whether it's elastic or inelastic. Momentum will always be conserved, providing there are no external forces acting on the objects before the collision. So when objects are free to move in two dimensions, you can continue to use the same rules as before. So the total momentum, that's the sum, that means total. That means the momentum, mass times velocity, but in the x direction. So the total momentum in the x direction is equal to the total momentum in the x direction after the collision. So the total momentum in the x direction before the collision is equal to total momentum in the x direction after the collision. The total momentum of the object before the collision in the y direction is equal to the total momentum of the objects in the y directions after the collision. And the second statement that we need to consider is for elastic collisions, kinetic energy is conserved, but we do not look at dimensions specifically in terms of x and y. We don't separate them out as we've done with the momentums. We use the magnitude. So we look at the overall velocity of the object. So the total kinetic energy before the collision is equal to the total kinetic energy after the collision for an elastic collision. Now, if it's an inelastic collision, this total kinetic energy before is greater than the total kinetic energy after. Now, we will look at this in a little bit more detail as specified by your syllabus. So here, because we are looking in with momentum, X and Y components, and then with kinetic energy, we are looking at magnitudes. We should be considering both Pythagoras and trigonometry. And it may help you to answer questions in a number of different techniques. But what I'm going to do is I'm going to look at a specific technique which I feel is best. But if you find another technique, that's absolutely fine. Okay, so these notes here, you say the total momentum in each direction must be the same before and after. And if you were to find the kinetic energy before and after, if it's the same, it's elastic. If it's not, it's inelastic. Now, I want to go to this specific example. And I've skipped this stuff in between that I've scrolled past. Now, what you've got is two objects. Object A colliding with object B. Okay, so you have got object A making its way to object B, slightly off center, and after the collision, object A moves off in this direction, object B moves off in this direction. This is the mutual collision point of both A and B. Now, that point should be literally on that surface because that's where the collision takes place. So there's that's a slight mistake. So that should be shifted right where the collision, where A directly hits B. So what we've got, let me just repeat that, a hockey puck on a frictionless air track. If it's moving to the right at 5 meters per second, it's going to continue to move to the right at 5 meters per second. The surface that it's moving along is not going to slow it down. If it was the case that this object was moving to the right and it was slowing down before it got to B, then we've got this external force idea included in our collision. So therefore, we cannot consider the total momentum before equal to the total momentum after. To do that, we must consider all the particles in the system. So the particles that are on the surface must be included for completing the conservation of momentum. Momentum is always conserved. Now, we need to have every body that's in the system to be accounted for. So, moving back to the example. So we've got object A move towards object B. Object B is not moving. And it collides with object A collides with object B. Both pucks have the same mass of 0.1 kilograms. Puck A moves off at 2 meters per second at an angle from the horizontal of 30 degrees. Object B moves off at some angle theta and some velocity which we don't know. That there is a vector notation, and that's the velocity of B. Now what we are going to do is we are going to find out what this angle is, what this velocity is, and we are going to figure out whether this collision is elastic or inelastic. So I'm going to move away from these notes. I'm going to answer